Apologies. The previous video, it cut out at question 11, had some network connections. I'm just going to continue with this as a part 2 of that video. You see in question 11, what's happened. In this question, you got a graph of natural log k, let's highlight this, against 1 over t for a reaction, and the gradient is given as minus 4420. So we know that y is equal to mx plus c. We learned that in GCSE. And you've got the format of the Arrhenius equation, the natural log taken of the Arrhenius equation in the y equals mx plus c format, like so. So the gradient is actually then EA minus EA over R. EA being the activation energy, which it wants you to work out. So all we do, we got minus 4420, which is your minus EA over R. If we multiply that by minus R, that gives you EA. So let's multiply that by minus 8.314, which is the gas constant, and that will give your answer in joules per mole. We want our answer in kilojoules per mole, so we're going to then divide that by 1,000. So let's put that in here, divide by 1,000, and that gives us kilojoules per mole. So minus 4420 times minus 8.314 divided by 1,000. That gives you 36.7 positive. And the mark scheme supports that. If you forgot to put the minus in here, you would have got B answer, which is wrong. So please be careful of that. Yep, we have our answer. Next question. The equation shows the dissociation of acid in water. Which pair is a conjugate acid-base pair? You see the word conjugate. I don't know the Oxford Dictionary meaning, but it basically means they are the same thing, but two different versions of. So really, my understanding is that it can't be any of the first three, because it should be the same thing, missing or gaining a H plus ion. So each of these three pairs, they're not the same thing with an H plus missing or gained. Only the last one, H3O plus. Here is your acid, and H2O is then acting as a base. So here, let's highlight this. This here and this here are your conjugate acid-base pairs. And the mark scheme supports that. D. Moving on. What is the number of stereoisomers that this ligand can have? You know what? Stereoisomers. I'm just going to quickly check. I want to give you a bit of a definition here. Stereoisomers. Now, stereoisomers are compounds with the same structural formula, but with different arrangements of atoms in space. Now you see, there's two types of stereoisomers. There is cis-trans, and there's also optical. These all come under the stereoisomers umbrella. So when you've got a complex ion that has two bidentate ligands and two monodentate ligands, I think the charge is neutral overall. This can you've either got your cis-trans version, so this is the cis version, and the cis also has the mirror image of it is the optical isomer, or you can have the trans, if you swap this to here, you've then got the trans version. So you're going to have the cis version, you're going to have the optical isomer of the cis, and then you've also got the trans. So you're going to have 3 different stereo isomers. Ladies and gentlemen, if you've been following these questions, you'll have noticed that this type of question has come up a few times. Many of the questions come up again and again. There will be many, many, many questions, but the answers tend to be the same. I really hope you've been following these questions, because they keep on getting repeated. B. Last 2 questions. Which properties is or are correct for transition elements? You see, with transition elements, the element has an atom with a partially filled d subshell. No! It's not atom, it's ion. It should read as an ion. So 1 is no. The existence of more than one oxidation state in its compounds, more than one oxidation state. Yep, we're happy with that. The formation of colored ions, yes. So it should be 2 and 3 only. And that is the answer. And can you see, ladies and gentlemen, how easy it is to overlook that word? It must read as one of its stable ions that has a partially filled d subshell. Partially filled d subshell. While we're here, let's give an example of that. What could be an example of that? Partially filled d subshell. You see, copper has got a 3d10 4s1. And so copper, a Cu2+ ion, has a 3d9 subshell, 9 electrons in the 3d subshell, which is partially filled. Whereas zinc is 3d10 4s2. Zinc can only form a 2+ charged ion. That means it's got a completely filled electron d subshell, and means this can't be a transition element. Last question. This is to do with 4 redox systems relevant to hydrogen-oxygen fuel cells, where a substance is reacted with oxygen to form an electrical current in the form of these batteries, modern batteries. Again, it's so easy to overlook certain words. What statements are correct for an alkaline hydrogen-oxygen fuel cell? The key word here being alkaline. For an alkaline, we will be looking at redox, this and this. So the reaction at the positive electrode is saying, will it be this one? No, it will not be. Because there's no alkaline species in there. It's not generating the alkaline, or it's not using the alkaline, the OH-. So it can't be the first one. The overall cell reaction, yes. Hydrogen reacting with oxygen to form water, that is correct. And the cell potential is 1.23. Let's have a look at these 2. It's going to be the more positive one minus the less positive one, or the more negative one. What does that give you? Yep, plus 1.23. So that's correct. So it's only 2 and 3, and the mark scheme supports that. The answer is C. Apologies for the technical glitch. I'll see you tomorrow.